Hello everyone, nice to see you again. Maria, we haven't asked you, do you feel okay if we record it and
Yes,
it will be uploaded to the...
Okay.
Yeah, it's all good. Dimitri, we've worked. It's all good.
Perfect. Today we have the second talk in the colloquium series for this year. And first of all, I would like to acknowledge the traditional owners of Australia land and pay my respect to the elders past and present, admonish the people of the Kulin nations. Today, I'm happy to present Maria Vozmediano, who is a research professor at the Instituto de Ciencia de Materials de Madrid, belonging to the Spanish National Research Council. She is one of the pioneers and leaders in Dirac physics in different setups, including fullerenes, graphene, and Weyl semimetals. Maria has recognized its beauty more than a decade before the graphene has been exfoliated and brought it from the high energy world to condensed matter systems. Maria, the stage is yours and we will enjoy the talk.
Thank you very much. Thank you all for coming. I will discuss today a topic that is very dear to me because it has to do with two aspects of physics that are very much the same, and but still they are very much apart now. So I'm trying to reunite this. These are quantum theory aspects of Dirac semimetals. I am been working on this with a set of collaborators. Here to the left, you see mostly young students. They are not so young anymore, neither am I, that were developing their thesis and their work with me on these topics. And those are high energy collaborators with whom I also has had some activity. I learned from them all very much. So let me start by trying to convince you that the electrons that we use in condensed matter around in the metal description of condensed matter, and these electrons that are out there in the free vacuum in the space, or the electrons that are in the accelerators, are the same kind of people. Let me start by something that you may all know, which is what I call the standard model of condensed matter. What is that? The standard model of the description of metals in condensed matter set by Landau, the so-called Landau Fermi liquid. This is Fermi and this is Landau. For metals, is something that is fantastic because it is able to describe all the metals or the Fermi liquid metals with a very single parameter. So it says all the metals will behave the same as conductivity or specific heat or whatever, and it will only be distinguished by a parameter that is called the effective mass. The most important aspect of a Fermi liquid or a metal is a material that has a Fermi surface. It means that when you do the band theory of the crystal that will constitute this metal, and you fill up the energy bands that you got, that you know that they are forbidden energy bands, gaps, and allowed energy bands mean almost a continuum of energy levels in the crystals. When you fill up these energy levels with electrons, you may end up in the middle of a allowed band. And if you end up in the middle of a band, what happens is this is the picture here. Your metal, because you have energy bands allowed as close as you will. So any amount of energy infinitesimal will allow you to jump to a empty band and to conduct electricity, heat, or whatever. According to band theory, you can also be a semi-metal when two bands touch like that. And then you are also described with an effective mass, which happens to be the curvature of the band. The brilliant idea of Landau was the idea that electrons in metals are in 1-to-1, the energy levels are in 1-to-1 corresponding to the levels of free electron gas, and hence have a dispersion relation, which is the one of the free electron gas, E equals to k²/2m, but the m, instead of being the mass of the free electron, will be a little bit heavier mass due to residual interactions. The most important aspect of then of the Fermi liquid is the ground state is the Fermi C, meaning that there is a layer, a Fermi energy here, and below there is all the states will be occupied. The main idea is that the states occupied will be more or less inert, and all the responsibles for the conduction and the properties of the metal will be, or all the fun of the metal will occur in a very thin layer around the Fermi surface. So what is a quasi-particle according to Landau? A quasi-particle is a excitation, a low energy excitation over the Fermi C. So let me summarize what I've said very fast. The two important aspects to me is first, the ground state of a Fermi, Landau Fermi liquid is not what we would call the vacuum or the Fock vacuum, in quantum mechanics, is full of people. It's the Fermi surface. The ground state is the Fermi C. And the quasi-particles are excitations over this field Fermi C. The description of the Landau Fermi liquid is a non-relativistic description in the sense that this dispersion is the non-relativistic standard dispersion, both for metals and semi-metals. So the first question mark is, what would happen if two bands would cross like that? Instead of touching like this, you would have a semi-metal where the bands cross and the Fermi level sits exactly at this point. There will not be a description like the Landau of k²/2m. There will not be an effective mass because the second derivative of this band, linear band, will be 0. So it's a question mark of what will happen to these people, and these people will be the starring of this talk. Please interrupt me anytime with questions if you wish, because this is a colloquium and I will be very happy to answer any question. So, ground state, which is called vacuum in the high energy context, is full of people. Quasi-particles are low energy excitations over this Fermi C. Now, let me tell you what are quantum field theory fermions. How do you set this quantum field theory fermions? The fermions in quantum field theory obey what is the Dirac equation. Quantum mechanics is just set by the Schrödinger equation, which is an equation of this type that says that the time evolution of the wave function is driven by the Hamiltonian, and the Hamiltonian is again p²/2m. This is written in derivatives here, but this is a non-relativistic p²/2m Hamiltonian who set by Schrödinger to describe the quantum mechanics systems. Now, at the time when the quantum mechanics was building up, special relativity also arose. And special relativity, says that energy and momentum are related linearly. So energy and momentum, or space and time, are the same thing. If you look at the Schrödinger equation, you see that time enters linearly, while the momentum, which is these two derivatives, is p², is quadratic. So Dirac was trying to combine both things, quantum mechanics and special relativity, trying to set up an equation for the electron that would be linear in momentum and in energy. So it wasn't an easy task. he got the Nobel Prize for it, as well as Schrödinger. The price he had to pay was that to have a multi-component wave function. So the wave function was no more a scalar field. It was, in particular, in 3 dimensions, 3 plus 1 is a 4-dimensional spinor. And he had to introduce some matrices, which are the Dirac matrices. But it doesn't matter. What is important is that the fermions, the Dirac fermions, are solutions of a matrix equation that is written in such a way that it is relativistic and quantum mechanical. Notice that there is a mass here as well as here, but the way the mass enters in the equation is very different. Here you can put the mass to 0. Here you cannot, and that's a classical hint of relativity. In relativity, you can't have 0 mass particles. You cannot have this. Sorry. In classical mechanics, in classical or quantum mechanics, nobody has 0 mass, right? Because you don't have description of massless particles. So that's a signature of relativity to be able to have 0 mass. Now, the minute that Dirac said his equation, it was obvious that the Dirac equation had negative energy solutions. In fact, there was an infinite tower of negative energy solutions. So this did not discourage these people to continue with this equation. They were really genius at that time. So they decided that, okay, let's establish that the vacuum of the ground state of our theory will be the infinite field Dirac. I mean, all the negative energy solutions levels will be occupied, and then we set up the vacuum as this place where everybody's occupied, this cone of the negative energy states is occupied, and an electron will be excitation over this Dirac. That sounds familiar with what we described before in the Fermi liquid, right? Because we have the same idea. It's a ground state or vacuum, which is full of people, and particles are excitations over this C. So now I come to my point. My point is particles and quasi-particles are elementary excitations, low energy. Well, particles that don't need to be low energies because the Dirac is infinite. But anyway, particles and quasi-particles are elementary excitations over the Dirac or Fermi C. What is the difference? The difference is that the Dirac is infinitely deep, while the Fermi C is compact, has like the swimming pool. But since everything occurs at low energies, I mean, since all the properties are occurring in a thin layer around the Fermi surface here, you will never see what is the bottom of your swimming pool. You will never see how deep it is because those states are inert down there, right? So I come to my main point is that same equations, same solutions. Particles and quasi-particles, fermions, have the same description. If there is any question at this point, that's a good point to ask questions. If not,
do you have any
I'll
questions?
continue. Yes, sorry.
Do you have any questions? Please just go ahead.
Okay. So my next point is now that we more or less know what the fermion is, both in high and in low energies, we will introduce a different kind of fermion, not a Dirac fermion, but something called Weyl fermion. So what is this? This is a Dirac equation that has this relativistic dispersion and has a mass, which is this gap. Now, this is an exercise for the students. If you write this Dirac equation, choose the Dirac matrices in the Weyl representation, you will see that the Hamiltonian of your system, which is you set up the Schrödinger equation, there is a Hamiltonian equal to this thing, and you will see that this Hamiltonian is diagonal and has off diagonal are the masses here. Now, if the mass of the system is 0, if this is dispersion relation, the mass lowers as to be 0, then you end up with these crossings, right? Where the energy dispersion is E equals to plus minus the velocity of light, P, the modulus of the momentum. And the Hamiltonian corresponding to this massless situation is a block diagonal, and it has a 2 by 2 blocks here, are described by sigma dot p and minus sigma dot p. Those people that have and this sigma dot p means that the spin or helicity is aligned in the direction of the momentum, or anti-aligned, meaning that these particles have a chirality, and these two sub-spinors have opposite chiralities. So what is a Weyl fermion? A Weyl fermion is a massless Dirac fermion in 3+1 dimensions that, since it is massless, has split into two component Weyl fermions of well-defined chirality. So what is a Weyl fermion? Is a single chirality, is a 2 by 2 spinors in 3 dimensions, X, Y, and Z, and T, that has a well-defined projection of spin or pseudo-spin or whatever on the direction of motion. This is a Weyl fermion. Now, are there Weyl fermions in nature? In elementary particles, there are no Weyl fermions because neutrinos that were the candidate to be Weyl, where we know now that they have masses, so they are not. But this did not discourage the high energy people to describe all the properties of these non-existent particles, maybe for the fun of it, or maybe because they devised a way to accede to these particles, which were, they had two main labs. The so-called quark-gluon plasma in heavy ion collisions, meaning you splash two heavy ions, and for fractions of a second, you get a very thick plasma of free. The quark-gluon plasma is, the nucleus is not only the nucleus is separated into protons and neutrons, but also the protons and neutrons are separated into its quarks, into its constituents. So all you have there is quarks and gluons and electrons, obviously. The electrons are not massless, neither are the muons or whatever you have, but the typical energy of the system is so high that the mass are negligible, and then you can access or you can predict the physics of these Weyl particles. Another lab for studying this in the high energy context is the early universe, where it happens the same. The universe was so hot that massless were negligible. Of course, you can imagine that these are not very fair experiments. I mean, it's not labs that anybody can access and study this Weyl. But it has happened recently in condensed matter that these particles that I told you that have linear crossings appeared, and the Landau quasi-particles around these crossings are exactly Weyl fermions. So now you can access experimentally in a much easier way or much lower energies the properties of the Weyl semimetals that we will discuss in what follows. I must say that both are effective theories, of course. This is theories that are, neglect the masses as compared with the energy, while here you will have this linear description only in a diffraction of energy until the band stand to bend. So it will be like in the case of graphene, for instance, that is the first material with band crosses that was popularized, is a very large, it's an effective theory for a large region of energy, is one electron volt or so, because the bands are really linear in 2+1. While these Weyl semimetals that I will describe have hundreds of milli-electron volts as effective theory. Still, they allow us to check some very interesting properties that I will tell you about. As a digression, since I was talking about fermi-liquid and I say that these people do not enter the paradigm of fermi-liquid, you may ask yourself, are they or not fermi-liquids? The answer is a yes, a very interesting yes, which is not the subject of this talk, but the important thing of the fermi-liquid is that interactions do not play a role. They are like marginal interactions. There is no relevant interaction in the fermi-liquid due to the screening of the Coulomb interaction by the Fermi sea. The same thing happens in this description in 3+1, where you can see that the Coulomb interaction is marginal, and the rest of interactions, short range, Hubbard, whatever, are irrelevant. So these particles also behave as free particles, only the dispersion relation is not a free dispersion relation like P square over 2m, it's just a linear dispersion. Okay.
Could I interrupt you?
Yes, of course.
So for this linear dispersion, the density of states, it is vanishes at these nodes and is small in their vicinity. Could we expect that they would be a better Fermi liquids compared to the conventional material with the parabolic dispersion?
I'm sorry, I'm trying to raise my microphone because I hear you very low. I cannot.
In the vicinity of the Weyl nodes, the density of states for electrons is small and vanishes at these special points.
That's right.
Could we anticipate that they would be a better Fermi liquids? Because if you don't have states, you don't have ability to scatter. Even better Fermi liquids compared.
You're right. The point here is that how do you define a Fermi liquid? In the sense that, let me see. Okay, I'll go back to this. The Fermi liquid, to me, is a free description, right? It's like I had a free Fermi gas, and then I went to a metal, and I found the same quasi-particles. Quasi-particles behaving the same as free electrons. So the very important thing is that because of as you say, because there is a density of states at the Fermi energy, the main interaction between the electrons, which is the electron Coulomb interaction, is screened. Now you say in the Weyl semimetals, since the density of states is 0 at the Fermi level, then so nobody screens the interaction. That's true. But it so happens that the Coulomb interaction is marginal. If you do an energy analysis of this interaction, even though it's not screened, still is marginal. And then it will not change the nature of the system. It will not change the vacuum. So Weyl semimetals have quasi-particles that behave exactly as free electrons, only they are massless, right? So that's what is different from the standard electrons. They are Weyl electrons or massless Dirac electrons, and interactions will not generate a different vacuum or will not generate a spontaneous symmetry breaking or a phase transition. Does this answer your question?
Yes, thank you.
Okay. So we say that there are two labs here that they do exist. I mean, this quark-gluon plasma is there's a lot of activity around it, and they are getting results that I will tell you more about later. And of course, this let me tell you about the existence of and the physical reality of Weyl semimetals, because this is a fascinating story. The first, we could say that the first Weyl semimetal is graphene. Of course, before graphene, there were other people, but say that the condensed matter community became aware of these Dirac materials with graphene. Only graphene is a little bit different, as I will tell you later also about it. But what did really made the revolution in this subject was the advent of 3+1 Weyl semimetals, 3+1 band crossings, right? So it's curious to know that the first that appeared in the 2015 was a photonic crystal that is this dispersion relation with a band crossing. But quite immediately there appear full families of decalcogenides, and there were this tantalum arsenide is the most common, but this niobium phosphide, and there are many people here. And on the 50s, that was when all these materials were developed. There is a special issue where you can read all about them, a special issue of Nature Materials. More recently, the interest has turned into what's called magnetic materials of these compositions, which are very interesting because they break time reversal symmetry, and as you see, they have properties that are even more exotic than the previous one. So again, in this review of 24 this year, February, there is an update of what has happened in all this in this 10 years almost. Okay, I must tell you that unlike topological insulators, these Weyl or Dirac semimetals are abundant and stable, so they are easy people to come to the labs and to make experiments with. Let me distinguish this Dirac matter into two types. A Dirac semimetal is a system where the two chiralities lie, as I described before, in high energies. In high energies, there is no other possibility. The two two-dimensional spinors, Weyl spinors, lie in the same point in energy and momentum. But it so happens in crystals that you can break in inversion or break in time reversal, you can split these two chiralities. And this is the most fascinating thing. And this has not happened in high energies. So you can have a single chirality separated from the other one. And then you can really explore this, the properties of these people, okay? You can also, starting with a Dirac semimetal, generate a Weyl semimetal by introducing a magnetic field that also breaks time reversal, of course. And the typical families of the Dirac semimetals, this zirconium pentatelluride is abundant and easy, and everybody has samples. Has a little gap, but it doesn't matter. The gap is very small, and it behaves as a semimetal. And then this sodium bismuth nitride and cadmium arsenide are very good, very stable Dirac semimetals. And Weyl semimetals, as I say, is the most common are this family of decalcogenides. The description of these Weyl people is a 4x4 Hamiltonian, as I said before, with different chiralities, this plus and minus sign in front of the sigma matrix. And if the two cones are separated in energy, then you will have this separation, energy separation, this B here in the Hamiltonian in this form. I may come back to that later. So now a question is, we have seen that before, because this was graphene. Graphene has the 2K and K prime points separated in momentum space and described by exactly this Hamiltonian, only in 2+1 dimensions instead of 3+1. So the question, which is a fair question to ask is graphene a Weyl semimetal in 2 dimensions? Why the node separation vector plays a role in Weyl semimetals that I will tell you about, and didn't ever play a role in graphene? What is topological in Weyl semimetal that is not in graphene? So I now come to one of the central parts of the talk, which is the main difference between 2- and 3-dimensional massless Dirac people is the chiral anomaly. So let me tell you a little bit about anomaly-induced transport in topological semimetals, theory, and experiments. Here again is a merging of these 2, condensed matter and high energies. I have to start by reminding you that, this is Emmy Nether, and this is what Einstein thought of her. That's an advertising. The most significant creative mathematical genius that's far produced since the higher education of women began. Why was she considered a genius by Einstein? Mostly because she set up a theorem that has been the basis of many aspects in physics. And the theorem says that if the action of a system, and when I say action here, I mean a classical action, mechanics, quantum mechanics, includes even statistical mechanics, the action of a system is invariant, has a continuum symmetry transformation, then there will be a conserved current and a conserved charge. We all know examples of these. Translations, if translation space is a symmetry, linear momentum will be conserved according to Nether. If time translation is a symmetry, energy will be conserved. And there is a less well-known symmetry transformation, which are gauge transformations, which are in quantum mechanics, when you have a wave package, a wave function, which has a phase, you can always rotate the phase, as you know, and this is a continuum transformation, and a transformation of this type is responsible for the conservation of electric charge. We can color in if you have more types, but okay. So this is the Nether theorem. You have a symmetry, you have currents and conserved quantities. Now, what is a quantum anomaly? An anomaly occurs when the classical action is invariant under the symmetry transformation, and after you quantize, this symmetry is lost. How can happen? How can this? Let me tell you an example of chiral anomaly. I told you before that the massless fermions split into left and right particles into these 2 chiralities that I told you about. So the classical action, this action is very fancy. Don't look at it. It doesn't matter. Just take in mind that you have left and right fermions because you are massless and you are in 3+1 dimensions. And then the classical, the Hamiltonian of the Dirac of Weyl particles is invariant under independent rotations of left and right fermions. That originates to currents, left and right currents, or the number of fermions in left and right is conserved. Normally, we define the 2 currents which are not left and right is the vector current, which is the sum of left and right, and the electric charge, or the number of electrons, in fact, is the sum of left and right, and the so-called axial current, which is the difference between left and right. So instead of having left currents and right currents, we have the sum and the difference, which is vector and axial current. So it is a fact of life that the quantum system cannot keep both. When you quantize, and I'll tell you now why, one of the two charges you have to give up. And of course, normally you will give up this actual current because the vector current implies conservation of the electric charge, which is a very holy paradigm in nature. So the divergence of this vector current will stay zero in the quantized system, while the divergence of the axial current will acquire a divergence which is proportional to E dot V. In the presence of an electromagnetic field, there will be this anomaly, and the axial current divergence will be proportional to the scalar product of E and V. The question is why? And there are two main questions here is, what is the origin of the anomalies, and why would anomalies induce new transport, which is where I really go. The origin of the anomalies is that when you quantize a system in quantum field theory, where there is infinitely many degrees of freedom, you go from Poisson brackets to commutators of operators. For instance, you have two wave what would be wave functions in quantum mechanics. We are now fields in quantum field theory. The commutator has a delta function here. Now, a current normally is the current, for instance, the electric current is psi daga gamma mu psi. So it involves two wave functions at the same point, are local currents. So local currents imply that there are two delta functions at the same point, and then you need to regularize the thing because two delta functions cannot be at the same point. So there are ways to define the current as a regular. For instance, point splitting is the more normal. You put one fermion in X and the other in X plus epsilon, define the current as the limit when epsilon goes to 0 of this psi X plus epsilon. Now, what happened is that the definition of quantum anomaly is there is no regulator of these currents or composite operators that keeps the current of all the conserved quantities conserved. Okay, so the response, say the origin of these anomalies is going from Poisson to Heisenberg. Now, why would anomalies generate unusual transport phenomena? It's because when you do a transformation of this quantum theory, you introduce, and you are anomalous, if not, the action remains invariant. The quantum action is as the classical action. You do this transformation, a rotation, or a phase, and remains the same. But if you are anomalous, then the action acquires new extra terms. And then once you have extra terms in the action, you can generate currents, extra currents. For example,
could I interrupt?
The actual, yes.
At which step it become important that we have 3 dimensions or 1 dimension? Why it's not possible when we have even number?
Exactly. This is very important. Thank you for reminding me. Maybe I was going to say it later, but I say it now. That's the main difference between graphene and these Weyl semimetals. There is no chiral anomaly in 2+1 dimensions. So you can remove the energy separation in graphene, which is a parameter that acts very much like an axial gauge field without any consequences. While if you try to do that in 3+1, you will generate this E dot V term in the action, and then you will generate the action electrodynamics. Okay, so in particular, let me continue with this. Nielsen and Ninomiya not only set up a theorem saying that the chiral fermions will always appear in pairs of the opposite chirality, so the full chirality will be 0 in the, say, in the Brillouin zone or in the system, but also say that in the presence of a parallel electric and magnetic field, they will be charged pumped from left to right. So you start by here, you put a magnetic field, and then this is the Landau level structure of these Weyl semimetals. There is a zero energy level, a zero mode of the Landau level, zero Landau level that you also don't have in non-relativistic systems, in Fermi liquids. There is no zero Landau level. Here it is. And if you then add an electric field, there will be charge pumping from left to right. This, in turn, generates a large negative magnetoresistivity that is locked to the B field. Means that when you analyze the magnetoresistance and you change the direction of the E with respect to B, or vice versa, B is easily to move, then you will see that there is an enhancement of the conductivity when E and B are parallel. And this has been, so the prediction is that when B is large, there will be, the magnetoresistance will be proportional to B. When B is small, and then there are many Landau levels involved in this transition, then there will be a B squared dependency of the magnetoresistance. That's a prediction that was set up in 83 when there were no Weyl semimetals or nothing of the kind. And let me now go and remind you how are real materials. Well, the description I made from high energies is two cones, perfectly straight, wonderful, sitting here, sitting at different places of the brilliant sun. And what happened in reality in crystals is that first there are many pairs of Weyl nodes. Normally in this tantalum arsenide, I told you there are 12 pairs of nodes. The cones are very anisotropic, so there are the section is not a circumference circle. It's the velocities around the different directions of the cone will be different. Also, very often they are tilted, the cones, so they are not straight. There are Fermi arcs. The Fermi surface in real materials life is hard, is never at exactly the Dirac point. So normally these systems are a little bit doped, either electron or hole. And even worse, there are trivial bands crossing the Fermi energy. So these are bands of one of these material. It's a mess, but if you open it, then you will see that near zero, there is these crossings. There are these crossings, but there are also other people. Well, here you don't see it, but there are also other trivial bands. And we would say that the hope to observe chiral physics, this chiral physics that seems so neat and so associated to, I have two cones at the Fermi energy, is hopeless. Nevertheless, quite immediately after the appearance of these materials in 2015, there appeared a plethora of articles saying observation of the chiral anomaly, signatures of the chiral anomaly, blah, blah, blah. At the beginning, this was controversial because there were other, so what do they see? They see this is the the increasing of the magnetoconductivity, and this is the angle between E and B. And then what you see is when E and B are parallel, there is an enormous peak associated to this magnetoresistance, which is what Nielsen and Ninomiya had predicted in the 80s. Now, there were also articles saying that this is, you don't need these Weyl cones and Weyl and chair numbers and so on in order to have this increasing, because there is current jetting and other more mundane effects that will mimic this thing. To me, this controversy is quite set, and there are more recent articles, this is in 22, 21, and so on, with different probes, which is not just measuring the magnetoresistance. There are terahertz spectroscopy and well, this mostly is that. in new materials which are cleaner and have better properties. And I think that there is a fact that this chiral anomaly is seen in these materials. That if you're interested on this topic, there is this review of Huang Ong, very recent. This was in the Nobel Symposium about chiral matter a year ago, 2 years ago, where he discusses very seriously all the possible origins of this phenomena, and he discards most of them. Okay, now, so far I've been discussing things that involve quantum field theory and condensed matter. Let me now come to a different form of anomalies, also only existent in 3+1 and 1+1, which is the mixed chiral gravitational anomaly. And this has to do with heat transport, and with gravity. And there now, on top of the two people that we had before merging quantum field theory and condensed matter, now we will have joining the play relativity and cosmology and thermodynamics. So this starts to be fascinating. What are the gravitational anomalies? You see, the divergence of the G5 of the axial current has a contribution from electromagnetic fields that is put in a very fancy way here. This is the topological thing and very interesting. But anyway, for you, this is E dot B. But in the presence of gravitational, in the presence of a curved space-time, there is a contribution to the axial anomaly coming from the curvature of the space-time. This, if you compute this electromagnetic origin of the anomaly, is this triangle with two vector currents and an axial current, while this one has two metrics and an axial current. Anyway, to our very, excitement, and it was like, no, how is that possible? Recently, or in 17, also very soon after this chiral anomaly was set up, it appeared this article, Experimental Signatures of the Mixed Axial Gravitational Anomaly in the Weyl semimetal. And then later it appeared this one also, which is very much the same. It says thermal chiral anomaly. Thermal chiral anomaly does not exist, but what they measure is exactly the same. Is thermoelectric transport in a magnetic field, so similar to what happened before. But now you have, instead of E and B, you have a gradient of temperature and E and B. And then you see that there is the thermal current is enhanced when the gradient of temperature is aligned, is parallel to B. This is the signature of this gravitational anomaly. The signature is a T-squared term in the conductivity that is exactly what is predicted by this term here in the action. Okay. So the question is, what is that? I mean, this is really very strange. First, because there is no curved space. I mean, in the lab where you have your samples, there is no curved space. So what is this gravitational anomaly doing here? And the origin, this is to me, this is the most fascinating part of this story. The idea is, how do you relate thermal transport with relativity? And the answer is quite obvious. If you see what the Einstein equation, general relativity is, it says that the curvature G mu nu is proportional to the energy momentum tensor T mu nu, right? And in the energy momentum tensor, what you have here in this corner is density, energy density, and moving energy density produces an energy current. And energy current is what is a thermal current, right? So in the energy momentum tensor, is the energy currents and densities are natural. The second aspect of it is you generate, when you have an action, you generate the currents just by adding sources and then deriving with respect to the sources. This is linear transport, no? And then if you see what drives the energy momentum components, this is the derivative of the action with respect to the metric. So in particular, the G00 will give rise to a density current. So thermal transport and gravity are very naturally related by this equation. Now, most mundane thing. You know that when you have a conductivity, there is a very standard way to compute the coefficients, the conductivity coefficients, which is Kubo formulas. And the Kubo formula says essentially, for instance, for this electrical conductivity, is you can compute it as the commutator of two currents, right, in linear response. Now, for that, you need a source, you need an electromagnetic field that you send the signal, you remove it, and then you see what happened to the system, this perturbation, and the system may generate the current. The point is, if you try to do this description for thermal currents, what will be your field? What will be what ignites the thermal current? Because gradient of temperature is a statistical quantity, is not a local, field that you can switch on and off. Temperature is a statistical thing, and there is not a local field. So there was at the in the 30s, again, a wonderful time, quantum mechanics, general relativity, and this. Tolman and Ehrenfest were asking themselves, this is unrelated, is what will be the equilibrium condition, thermodynamic equilibrium in a curved space, in a gravitational potential. And then they discovered that if you are in a gravitational potential, what stays constant in the equilibrium is not temperature, but is a combination of temperature and gravitational field. So is the gradient of temperature plus gravitational field with what remains constant in a equilibrium in a curved space. So what they saw is the variation of gravitational potentials induce variations of temperature. And then it comes another genius of physics that I think is underestimated, but is amazing, which is Latinger. Latinger set up wrote a crucial paper in the 64 called Theory of Thermal Transport Coefficients, where he asked himself, can I set a Kubo formula for thermal conductivity? And the answer was he just was supported by this Tolman and Ehrenfest relation, and suggested that the way to generate thermal currents was by means of a fictitious gravitational field. So he in fact says that, in fact, if the gravitational field did not exist, we could invent one for the purposes of this paper. So it's not that Latinger wanted to be in the curved space. He wanted to use as a tool the gravitational field, and then you generate the current and you put it to zero. That is what you do in the response functions. So altogether, that's the way to relate general relativity and thermal transport. And I think that this is a highlight in condensed matter that, at least to my opinion, has not been appreciated properly. Now, let me discuss now another very interesting thing. It's a lesser known anomaly, which is the scale anomaly, for which the experiments are still lacking. There are people searching for it, but there are not yet evidences. And this is again a merging of quantum field theory, quantum mechanics, and condensed matter, and relativity and cosmology. What is this? What is the scale invariance? If you have a Hamiltonian, which has no dimension full parameters, meaning no masses, no coupling constant with dimensions, then your system is invariant under rescaling of all the lengths or energies or whatever, right? So there is a classical invariance in the massless QED in this theory of the Weyl semimetals, which is scale invariance. If you apply another theorem to this system, then you see that there is a so-called dilatation current, which is built with the energy momentum tensor like that. This doesn't matter, but the important thing is that the conservation of the current is linked if the energy momentum tensor is conserved, which we always assume, to the traceless of the energy momentum tensor. So if you have scale invariance, or Weyl invariance is also called, or conformal invariance, then the stress tensor is traceless at the classical level. Now we could ask what happens if we can quantize the theory. And then what happens is that some of the couplings, for instance, the QED coupling, the standard electric charge, when you renormalize, which is alpha dimensionless, fine structure constant, when you renormalize, it acquires a dependency with the energy. It is a running coupling constant. The coupling constant evolves in quantum field theory, and then this dependency on energy induces a conformal anomaly. This was studied in high energies by Maxime Chernobyl, one of my friends and collaborators, and he set up that due to this conformal anomaly, there would be an electric current proportional to the cross product of a magnetic field. And so if you had a scale transformation in the universe with a scale factor, conformal factor that was varying, that has a gradient, then there will be an electric current proportional to this gradient of tau dot v, and with the beta function of QED as a coefficient. Okay, so then we met Maxime, and then we saw this thing, and we proposed that you can trade this conformal factor by a gravitational field. That's something that can be done. And then you would generate a new Nernst effect, because you generate a current which is proportional to B gradient of T just by using the Tolman RFS Latinger trick of trading gravitational field, which is contained in this factor, by a gradient of temperature. So the prediction is that there will be a Nernst effect, or this thermomagnetic conductivity proportional to this beta. The beta function of QED is this one. So you end up having this. Since that was very exotic, because that would be a current at zero chemical potential and zero temperature, then we did a Kubo calculation of this effect, and we got exactly the same result. So the prediction, the experimental signature, is the thermoelectric coefficient should extrapolate to a non-zero value as t goes to 0 and mu goes to 0, should be linear in B and proportional to the Fermi velocity. So this is a homework for the experimentalist. Now, I'm sorry, but due to time, I will skip. Yes?
Could I interrupt you?
Yes, of course.
So when you have this thermoelectric phenomena, I think you have electric field and thermal gradient at the same time. So they coexist.
Yeah, yes.
How's this? So you have two terms, and they always will be present. One is proportional to the electric fields,
yes,
and the other one is proportional to the gradient of temperature. Is it possible to separate them, or do you expect that one of them is dominant, or if they can be comparable in some situations?
Well, what I think is that the experiment will probe one or the other. For instance, all these chiral anomaly experiments are magnetoconductance with zero gradient of temperature, right? And then you probe the electromagnetic contribution to the chiral anomaly. Now, if you put the gradient of temperature without an electric field, then you get this contribution, this gravitational anomaly. So no, there is no electric field in the experiments of let me see. We're talking about this. So what they compute is just magnetic field and gradient of temperature. There is no electric field here. And then you can disentangle the two things. Plus, you see the effect is very interesting because the effect is, you see exactly as we saw in the chiral anomaly, they see a peak in the thermomagnetic conductivity when B is parallel to gradient of temperature. So it will be a very similar curve to this one, but here the angle is between the gradient of temperature and the magnetic field. So you, of course, have the two contributions, but I think it's easy experimentally to disentangle them.
Okay, thank you.
Okay, so I'll skip this, which is very dear to me also, because, but I don't want to keep you there the whole afternoon. And I'll come to other interesting developments, which is something that is very interesting also, is that these people are now showing hydrodynamic aspects. So they are seeing vortices and Poisson flow. They are measuring the viscosity. So and this is an absolutely fascinating topic that is going on right now, but I don't have time to go into it. So let me summarize why I'm so interested in this topic. This topic, I should put Emineder here in the middle. I'm sorry. This okay. This has betrayed me, this tradition of putting an element there. What we see is that this Dirac matter has made a grand unification between quantum field theory, condensed matter, statistical physics, that also condensed matter is statistical physics in many sense, the quark-gluon plasma, hydro, elasticity is this part that I skipped, sorry, about the elastic gauge fields, but it's so beautiful also, and relativity and cosmology. And I didn't tell you also about holography has models of the holographic Weyl semimetals, where they also studied conductivity sensing with holographic techniques. So with this, I thank you for your attention, and I end up.
Thank you for fantastic talk. Do you have any questions? Please just go ahead and ask. Let me start. So this Schlesinger trick, is it very generic? So it can be both applied for the conventional electrons and for the Weyl ones. So
oh yes. This Schlesinger trick was set up in the absence of any Weyl or Dirac or anything. It was in CSIC. So his leitmotif was he wanted a Kubo formula for the heat transport. So he needed a local field as a source of temperature of thermal currents. And then so he came out with the idea, okay, the gradient of temperature is not a local field, but the gravitational potential is, and then I will use this as a tool and generate thermal currents with it. So this applies totally, is totally general. And then he was able to formulate this it's not written here, but this alpha ij is as is this thing. There is a commutator of ji and the gravitational field J. Okay, so he set up a formula for the thermal conductivity exactly analog to this one, where where this gravitational field was there, and then he throws out the gravitational field.
Okay. Do we have any other questions? Please just go ahead. Be brave.
Yeah, I know that these things are very scary, but I tell you, it's a lot of fun, mostly but for youngsters, if they are young people, please study these things. It's a lot of fun, and it opens your mind. I mean, you discover so many different things that are essentially the same. It's wonderful. Looks difficult, but it's not. Mathematics are always simple.
Please just go ahead and if you have any questions.
Maybe I can ask one. Thank you for your talk. Can you hear me?
Yeah, I do.
So I must admit, I'm not sure I fully grasp this gravity. So it's not an analogy here. It's so the phi in this equation is supposed to be the real gravitational field, or is there like is it like an analog of?
That's a very good question. We are not in a gravitational field. Well, we are in a gravitational field, but the gravitational field of the Earth, the contribution was estimated to these people of this contribution to the thermal equilibrium in thermodynamics, and it was like 10 to the minus 33 or something like that. So although we are in a gravitational field, this is not the product of a real gravity. This is just a tool. So what do you do in response function to generate currents? You have your action, for instance, the electric current. You have J vector equal to the variation of the action with respect to A mu vector. A, I mean the electromagnetic potential, right? But then you say that this current is ds over dA, and when A is put to 0. So what do you do in response functions? You shake the material with a field, and then you put the source to 0, right? So Latinger thought, okay, I'll shake the material with a field that does not exist, but since I am putting it to 0 at the end, what do I care, right? And then he got this Kubo formula when without any gravitational field. So it's not an analogy, it's a tool, you know?
Yeah, okay. Okay. Thank you.
Mm-hmm.
I have a question. So all this possible only in Weyl semimetals that break time reversal symmetry. So it's
what?
So it all this magic happens when two Weyl nodes are are separated in momentum space.
No. When you say all these things,
I mean, all these anomalies or this transport.
Okay. So
they happen when you have time reversal symmetries.
You see for instance, the chiral anomaly, which is the mother of all the anomalies, that happened. That was, by the way, experimentally proved in high energies. And the signature of the chiral anomaly is the decay of the pi 0, this pion, into 2 photons that has a rate much higher than it should, and this rate is due to the chiral anomaly. So the chiral anomaly was experimentally confirmed in high energies where there is no separation between the nodes. That occurs also in Dirac semimetals, the chiral anomaly, okay? The things that occur only when you break time reversal are other things that are very interesting and I didn't go through, but all the things that I have described here, gravitational and chiral anomalies, occur, and also this conformal anomaly occur in also in Dirac semimetals. You don't need a space separation, or you don't need the Weyl cones to be separated in either space or time.
Okay, I see. Thank you. Okay, so if you don't have any other questions, or if I know if I want to just throw the last moment one. Okay, if not.
Okay, sorry, maybe just coming back to the gravity. So since we have the slide, just checking. So this approach of Luttinger has nothing to do with Weyl metal. So it is not even related with the anomaly. It is more general. Or
are we talking about this contribution to the thermomagnetic conductivity?
So, I mean, yes, or at least the origin is the paper from Luttinger. It was
okay.
Prior, as I think you mentioned, prior to, so it's not anormal, but then there are anomalous contribution maybe to this effect.
No. Thank you for the question. No, I've been messy here. So the setting, the thing is, they observe something in the experiment that they associated to the gravitational anomalies. Okay, so there is an experiment, and there are gravitational anomalies that were set up by quantum field theorists. So what I wanted to address was, what the hell? I mean, what is the connection between gravity and heat transport? And then I came to this Latinger, you see. So I have turned, I went to the past just to convince you that heat transport has very much to do with relativity and curved spaces, although you don't need any curvature to get this anomalous behavior, okay? So this Latinger thing, I think it's extremely important. I should go to the textbooks in condensed matter, but it was just a way to tell you why gravity has erupted into these condensed matter experiments.
Yeah, it was already there before, even before the anomaly. So maybe with some anomaly it can also show up, I guess.
Yeah, the point is that, yeah, well, I only wanted just to relate gravity with thermal transport. The experiments, what they see, in fact, is a contribution to this conductivity thermal, which was predicted in the quark-gluon plasma, and is difficult to explain with a standard condensed matter. So it's true, maybe this answered the previous question more accurately. It's true that in the interpretation of the experiment as contribution from the gravitational anomaly, this proceeds by analogy. What they see is that there is a term that is proportional to t squared in this conductivity, and this term was predicted in the quark-gluon plasma as a contribution from the gravitational anomaly, right? And the coefficient, well, the coefficient is very hard to set up experimentally, but there is a very precise prediction on the coefficient from the high energies. So this experiment is really an analogy. It's like, what is the origin of this field? I've seen that before, and I've seen that as a product of the gravitational anomaly, right?
Okay, I see. That's it. Thank you.
Okay, thank you. So let's thank you, Maria, again. And I see all of you in a month. So bye to everybody.
Bye, and thank you very much.